Hello, I'm Xueyang Li from the Institute of Information Technology, Chinese Academy of Sciences, and now I will introduce our work, TransRepair, which cooperates with the above organizations. First of all, let's introduce the background of our work. Current AI programmers, like human beginners, write erroneous code, which includes compilation errors. According to a statistical survey by CoreLogics, programmers spend on average 75% of their work time debugging programs and fixing errors. Therefore, developing an approach that automatically fix up compilation errors would be very valuable to improve programming efficiency. Someone may ask, doesn't the compiler tell us what error occurs while in the code? Why do we need another fixing approach? Yes, the compiler will output an error message when it detects the wrong code, just like in our diagram. But the problem is that the compiler doesn't always find the root cause of the problem. In this case shown, the error is due to the return type of the declared function be void. But void can't be returned as an if flag, and the compiler's feedback tells us that the error is on line 17. But obviously, if we want to fix the code, we should locate line 2 to fix it. So, how does a human fix the code? When a programmer finds a compilation error, he will first read the compiler feedback, determine the general location and the type of the error. Then, he will look for the relevant context, locate the specific error, and then fix the code at that location. The concept and algorithm of automatic compilation error repair is not our first creation. There has been some work in this area. Let's say these two algorithms, devise and repair, both use a neural network to repair the source code. The difference is that devise only uses the source code information over a sequence-to-sequence neural network. repair built a tool called Program Feedback Graph. It captures the content in quotes from the compiler message and builds a connection to the source code. From there, the information flows, and then the final fix is done using LSTM. However, they both have some weakness. For example, devise doesn't use compiler messages and contexts. Furthermore, it has very limited error types for training data. repair sometimes can't build a normal program feedback graph without quotes in compiler messages. Sometimes the program feedback graph doesn't capture the root cause of the error, and repair's training data has similar limitation in error types. Our goal is to learn a pattern for fixing programs from source code, compiler messages, and context. To achieve this goal, we will face some challenges. First, the existing dataset has a limited variety of errors. These data have not been fully evaluated. Therefore, it's not clear which types of errors are not well learned and their underlying causes. Another is the modeling aspect. First, how do we get the useful context? The code is long, but not all of it is useful for fixing errors. Then, there is how to connect context, compiler message, and source code. Finally, how to model the reasoning of repair. In the later slides, we will describe how we addressed these challenges. Here we show the overall structure of TransRepair. It's divided into three parts. First is data synthesis, then comes the data parsing. Finally, there is our repair model. In the first part, we input two real datasets and Stack Overflow questions to summarize 74 patterns and synthesize a new dataset of error codes. We input the new dataset into the data parsing section to obtain a joint representation of error codes, context, and compiler messages. Finally, they are fed into the model for training. Now, we introduce the first part of data synthesis, where we divide the error types in deepfakes, tracer, and Stack Overflow into two major categories and 5 subcategories, and we summarize 74 error patterns from them. We use these 74 error patterns to guide the generation of the new dataset in the following 3 steps. First, we analyze the correct code and obtain the feature of code. Look here. The descriptions of variables and functions here are what we call features. In the second step, we match these features with the corresponding error patterns. This is our list of patterns. We can find that pattern 2 can match, but pattern 74 cannot. And finally, apply the error patterns for corrosion and generate the error codes. That is, we will choose pattern 2 and remove the type of function pair. With these real-world patterns, we can generate more diverse datasets and address data challenges. The second part uses the error code obtained in the previous step and its context compiler message into a sequence, as shown in the figure. Look here. This is a line of code, and this is context. And this is the compiler message for this code, for this full code. And we stitch these 3 parts together into a sequence. The quality of the context will affect our model training. In order to obtain the correct context, we use the algorithm for context extraction. First, we perform a complete analysis of the input code to determine what variables, functions, and types it has. Then we will analyze it line by line to determine what variables or functions present in each line. For example, line 17, we use function pair variable s and I. Finally, we find the code of their declaration and the most recently used code for each function and variable mentioned in each line. For example, line 17. Its context is line 2, line 10, line 12, line 14, and line 15. With these designs, we obtain valid context and unite them with source code and compiler messages. The previous section constructs the input of the model. Now, we introduce our repair model, which is divided into 3 parts: encoder, localization, and pointer decoder. Starting with the encoder, which consists of an embedding layer and multiple transformer encoder layers that encode the input sequence as a vector hi. After obtaining the vector hi for each row, we input them into the MLP for localization, which can be considered a classification task, and output the error probability for each row. Well, the row with the highest probability will be edited later. As with localization, we input the vector hi into the point decoder to decode the new code. It consists of multiple transformer decoder layers and a point generator. Since the token of the test sample may be out of vocabulary, we need to use the point generator to copy some tokens from the input samples. The point decoder will first calculate the probability of generating token from the vocabulary, then calculate the probability of generating each token in the vocabulary and the input sequence separately. And finally, calculate the probability by combining the equation in the figure, selecting the most likely token. Then we will introduce the evaluation part. Before that, we first mention two research questions. The first one is how our TransRepair performance compares with existing approaches. And the second one is when TransRepair performs better and when it does not. We evaluated two datasets, devise and tracer, with a baseline of devise, RL assist, simple fix, doctor repair, and maser, all of which are better existing repair algorithms. To evaluate the performance, we set three metrics. The first is single localize, which evaluates the ability of the algorithm to find the location of a single line error. And then single repair, which evaluates the ability of the algorithm to repair the error when the location is provided. Since devise real code doesn't have ground truth, we test these two metrics only on the tracer test set. Finally, full repair, which evaluates the ability of the algorithm to complete locating and repairing the code when only the error code is provided. Regarding the first research question, we perform a detailed evaluation, and TransRepair achieves state-of-the-art result on both single repair and full repair, although we trained doctor repair and TransRepair using doctor repair's dataset and our dataset, respectively. And the results show that the model trained with our dataset have higher performance. This indicates that our dataset can help the model to improve the repair ability. Regarding the second research question, we compare doctor repair and TransRepair in 5 error categories. We found that doctor repair can fix identifier misuse better than TransRepair, which we believe is due to the fact that the program feedback graph uses a large amount of identifier information, which improves the fixing rate of this type of error. However, TransRepair still achieves a competitive performance, fixing only 5 fewer error codes than doctor repair. In all other 4 categories of errors, TransRepair fixes them better than doctor repair. Okay, finally we show you a real-world example of the error code that kept appearing in our previous slides. Doctor repair located the line of code prompted by the compiler, so it couldn't complete the fix. While TransRepair not only correctly located the error, but also generated the correct code on the first attempt to fix it. To summarize our work, there are four main contributions. First is a transformer-based algorithm, TransRepair, that can fix compilation errors. Second is our complete experiment on 2 datasets. The third is our summary of 74 error patterns from 2 public available datasets and Stack Overflow questions. And finally, our development of a data synthesis algorithm that provides a more diverse dataset. Okay, this is the end of our presentation. If you want to learn more about our codes, datasets, and more materials, you can visit the website. Thank you.